Hello and welcome to my talk on ticket prices in public transport. My name is Anita Schöbel and this is joint work together with Rena Urban, who did her master's thesis on this topic and will start as PhD student next month. I will first show different types of fare systems, then we will discuss properties of fare systems with the goal to find cheapest ticket options for the passengers, and then we will conclude. So public transport providers cannot live on air and love. They need income. This can be government or state subsidies or cross-financing, for example, if a public transport provider also owns gas and electricity facilities. But the most obvious thing is to collect fares through ticket sales, and that's what this talk is about. There are different types of fare systems common. The easiest one are flat fares, in which there is a unit price for every journey. Also common are distance-based fares, where you pay for the kilometers you spend in the bus or train. In Beeline-based fares, you also pay for the kilometers, but for the kilometers of the airline distance between your origin and your destination. In zone-based fares, the region is divided into tariff zones. You count the number of zones and you pay for the number of zones you pass. And for example, short distance tariffs can be added to give a discount on very short journeys. Note that fare systems should not be confused with ticketing systems. That is another thing where you can discuss if you would like to buy your ticket as paper ticket or electronically in ticket machines in the internet or just show your mobile. But that's not the topic of this talk. So these different types of fare systems are very common. Flat tariffs are used in cities. Distance tariffs are very common in most railway transportation in the world. And zone tariffs are very common in transport networks where different public transport providers act together. That is very common in Germany, but you also know them from London, Barcelona, California and other cities. The goal of this talk now is to compute cheapest paths in all of these fare systems. This will be done in 3 steps. You will first model the fare system, then see properties of the fare system, analyze and discuss them, and finally, hopefully, end up with algorithms. What literature is around here? Literature in the field of tariff planning is very scarce compared to other fields of public transport. There is a few papers on the design of fare systems, but today I'm going to deal with the computation of cheapest paths, and this has been included for distance tariffs in a paper of Müller-Hannemann and Schnee, and last year on the ATMOS conference we had this paper of Euler and Berndorfer, where they did that very in general fare systems with an exponential approach. In this talk we look at the computation of cheapest paths in the mentioned fare systems of the last slide. Now, the first step is to model the fare systems. We have given a public transport network as a connected, undirected graph embedded in the plane, and we are interested in the set of the paths through the public transport network. Because a fare system is a function, p, that assigns a price to every path in the public transport network. The price should be positive, since you usually have to pay something if you want to travel. A note is that the price is not only dependent on the origin and the destination, so on the start and end station, but it may depend on the whole path. Now we want to investigate 3 properties of fare systems: the No-stopover property, the No-elongation property, and the Subpath optimality property. Let's start with the No-stopover property. A path satisfies the No-stopover property if the price for the whole path from x1 to xn is always cheaper than the price for a subpath from x1 to an intermediate station xi plus the ticket price from this intermediate station xi to the last station xn. And a fare system satisfies the no-stopover property if it is satisfied for all paths. This means that if the no-stopover property holds, you never decrease the ticket price by a stopover. And if a fare system has the no-stopover property, then also multiple stopovers will never decrease the ticket price. The no-elongation property is defined as follows. A path satisfies the no-elongation property if the price for any subpath of a path is smaller, cheaper than the price for the full path. And a fare system satisfies the no-elongation property if it is satisfied for all paths. It means that buying a ticket for a longer path is never preferable to buying the ticket for the subpath you really want to travel. The subpath optimality property is well known to all of you. It is that every subpath of a cheapest path is again a cheapest path, and we know that if the subpath optimality property holds, dynamic programming can be applied. One remark, these three properties are not related with each other, so none of these properties follows from the other ones. Let's start with a flat tariff as a simple warm-up. A fare system is a flat tariff if the price for any path is the same, for example ρ. And when a flat tariff satisfies the no-stopover property, the no-elongation property, and the subpath optimality property. That's very easy to see because a stopover will not help if all paths cost the same. Making a path longer will not help if all paths cost the same. And since every path is optimal, the subpath optimality property is also satisfied. This also helps for finding a cheapest path. We can just choose any path between our origin and destination. It will be a cheapest one. It is again easy for the distance tariff. A distance tariff is a tariff where the price for a path W depends on a fixed price F plus a price ρ per kilometer times the length of the path. And also a distance tariff satisfies all three properties, which can be easily seen, and it is somehow the same thing as computing shortest paths in networks with respect to their length. So that is again easy to find them. Now we come to the Beeline tariff. A fare system is a Beeline tariff if the price for a path W is again a fixed price plus a price per kilometer times the Euclidean distance between the start station and the end station of the path. Now a Beeline tariff easily satisfies the no-stopover property and also the subpath optimality property. But it does in general not satisfy the no-elongation property, as you can see on this small graph which is graphed here. Suppose you would like to travel from x1 to x2, then the price would be 5, if the distance is 5, for example. But if you would buy a ticket from x1 to x3 and travel the path x1, x2, x3 and just get off on x2, then you would save money, namely the ticket price from x1 to x3 is only 4, also you traveled to x2. Nevertheless, finding a cheapest path is easy. We can again just choose any path because all paths with the same origin and the same destination cost the same. It's getting more complicated with zone tariff systems. For a zone tariff system, we need to introduce a function set of v that counts the number of zones entered by a path. So I have two examples here. Consider this path from x1 to x3 that passes through 3 zones, no matter if the zone includes stations or if it is an empty zone. And when a fare system P is a zone tariff with respect to a price function P that assigns a price to every number of zones you would like to pass, if the price for a path is just the price which depends on the number of zones you travel. Let's first look at the no-stopover property for zone tariffs. And here we have the following theorem. If a price function is given, then all zone tariffs with respect to this price sum function satisfy the no-stopover property if and only if this formula is satisfied. Namely, the price for traveling through k zones should be bounded by the price for traveling through I zones plus p of k minus I plus 1 for all k and all I up to k half. The interesting thing is that the no-stopover property hence only depends on the price function and not on the zones. Examples for price functions that satisfy this property is if a price function is decreasing, which is nonsense in practice because usually if you travel more zones you should pay a higher price, but also if a price function is affine linear. It is in general not true for increasing price functions. For example, if you pay 1 for traveling through 1 zone, 2 for visiting 2 zones and 5 euro for visiting 3 zones, then it would be better to buy 2 tickets with 2 zones instead of 1 ticket for 3 zones. Also, the no-elongation property holds if and only if the price list is increasing. That can be shown rather easily. And if you look at the subpath optimality property, then a zone tariff with a strictly increasing price function which satisfies the no-stopover property also satisfies the subpath optimality property. So these are three different conditions for our three properties, but if the price function is finally increasing when all three properties are satisfied. On the other hand, for arbitrary price functions as you find them in practice, you have to be careful. Now, how can cheapest paths be computed in zone tariff systems? The first bad news is that cheapest paths need not exist in general, but they exist if a price function p is increasing. And in this case, we can compute shortest paths by the following theorem, namely, if the zone tariff p satisfies the no-stopover property, that is important, and as I said, it's not always satisfied in practice, then if a price function is increasing, then any path between two stations with a minimum number of zones is a cheapest path, and if a price function is strictly increasing, then a path between two stations is a cheapest path if and only if it visits a minimum number of zones. That means that under these conditions, namely in the case of the subpath optimality property and an increasing price function, we can choose a shortest path with respect to the crossed number of zones, and this can be done by shortest path techniques. In practice, zone tariffs can be more complicated. They can have metropolitan zones, overlapping zones, or for example, zones may be counted only once even if visited more than once, and this makes things more challenging. Here's a small example with a metropolitan zone. So we have a lot of zones and they are used for counting paths between which go into the metropolitan zone or they pass the metropolitan zone, but within the gray zones we have one fixed price rho m, which may be high if the zone is attractive or low if public transport should be enforced in this zone. For such zone tariffs, the no-stopover property need not be satisfied. For example, if the price within the metropolitan zone, the gray zone, is the same as the price for traveling through two zones, it would be cheaper to travel from x1 to x2 with a ticket for two zones and then from x2 to x6 with a ticket within the metropolitan zone than buying a ticket for the 6 zones from x1 to x6. And this really happens in practice. We can show you examples. So it's quite interesting to discuss when the no-stopover property is satisfied for metropolitan zones, and here are some criteria. Look at the blue formula, which again only depends on the price list, or mainly depends on the price list. And in this case, namely if we have a subpath optimality, an increasing price function, and the price for the metropolitan zone should be smaller than the price for two zones, we can again solve this problem by shortest path techniques. So that is the first point for metropolitan zones. The no-stopover property does not always hold in practice. If we have overlapping zones, it's interesting that the no-stopover property holds if our price list is subadditive. And the cheapest path can be computed by shortest path techniques in a new graph that we call overlap resolved graph. And it gets particularly interesting if we count zones not only once, even if they are visited more than once, which is common again in many tariff systems, because then computing a cheapest path is NP hard. Details can be found in the master thesis of Rena. So what can be done in the future? We are interested in having more efficient algorithms for computing the cheapest paths. We would like to integrate cheapest paths in multi-objective route planning, so the price function, and we would like to integrate the whole thing with line planning. Also, it would be nice if we could use the ticket prices to control demand and avoid crowding, which might be in a particular useful in times of COVID-19 where we should not get too close to each other. And how this can be done, I might tell you about in the next ATMOS meeting. For today, I say thank you for your attention.